Hello everyone, this is my video for fraud detection using Benford's law. I will link the video for this worksheet after I finish making it. It does need Google Sheets. I'm sorry you don't like Google Sheets, but I'm sure when you're 30 or 35 years old, you'll benefit from this enormously. I was looking for a project where in one single hour, we could learn more about it than 99% of the people on this planet. And so few people know how to do this that this seemed like an ideal topic. And 1 hour is easily enough to get a good idea about what it means. After this, you will be able to identify fraud in lists of numbers, even if you only can see the numbers and know nothing else, even know how those numbers were acquired. This is what auditors and financial investigators have to do, but increasingly scientists and academic people have to review each other's numbers as well, because there's a lot of fraud going around, a lot of fraud. I've given you a couple of clips. The first one is fun, and it's from an actual film. The second one is an explanation of the maths of this, which I'm going to open up now. What Benford's law is telling us is something about this first number. So in the second column, we've just taken the first number. It's 2, it's 9, it's 1. We're just interested in that first number. And what Benford's law is telling us is this, that of any natural data, whether it's physical constants, rainfall, population, lengths of rivers, size of lakes, height of mountains, distance to stars, 30% of those numbers will start with a 1, and only 4.6% will start with a 9. Now, this is one of the most surprising things in mathematics, and very few people know about it. Why should more numbers start with a 1 than start with a 2? It just doesn't make any sense at all. But somehow it's true. This was spotted by someone called Simon Newcomb about 130 years ago. And it's called Benford's law mostly because Benford's famous for publishing about it. Well, there it is. I mean, that applies to anything except phone numbers or, say, the heights of people, because the shortest person isn't much shorter than the tallest person. It applies to any data where the smallest number is a lot smaller than the biggest one. And it doesn't apply to things like telephone numbers, which are given by people, or library numbers, or student numbers. It doesn't apply to those things. And it doesn't apply to random numbers, but it does apply to almost everything else. Okay. And when it doesn't, you're suspicious that there's some cheating going on, because financial data also follows Benford's law, and so does academic and scientific data. And if you find that in your data it doesn't follow Benford's law, there's probably something wrong. Probably. Right. My question is, what about diseases? Do they follow Benford's law as well? And if they do, would we be able to make any sense of what's going on right now? So I opened up, I did a search on this, and I opened up a couple of academic papers. One of them is there. Now, this is interesting. This is for actual COVID-19 cases in December. And they did an analysis on the number of new cases every day. And they found that it does follow Benford's law. So Benford's law are the blue circles, and the orange crosses are the actual case statistics. So according to this paper, the original outbreak in Wuhan does follow Benford's law, at least at the beginning. And that means that the Chinese data is not cheating. But is it only this? Is it only this? And the answer is no. I've also got a paper here about cancer research, and there's the important graph. It follows Benford's law almost perfectly. So some diseases, I can't say for all of them, but some diseases, the spread of those diseases or the incidence of those diseases does follow Benford's law. Okay. I don't have any data for COVID-19. So I've got population. I've got the population data already and Fibonacci numbers already. And the task for you is to see whether these follow Benford's law or not. This is the one I did for Birmingham University last year. Fibonacci numbers, they follow Benford's law absolutely beautifully. The Benford's law line and the Fibonacci line are together. That's why you can't even see the blue spots. But city populations, now these are UK cities. So I got 7,729 populations for UK cities. And I was interested to see whether the population count also follows Benford's law. And it does pretty closely. So these are actual cities, the blue ones, and Benford's law is the red circles. Pretty close. Okay, that's the completed one, but this is the one that I'm going to ask you to do. Don't do the cities from Birmingham or the random numbers. It's just these first two tabs that I'm interested in here. I'm going to type in some code now. If I type in left and type in B3, 2 to see what that does. Do you see that? Now if I change that to a 3, if I change it to a 5, you can see what that left command does. The left command takes the character or number or writing in that cell and gives you the first or the leftmost 5 parts of it. Well, we're not interested in the names of the cities, we're interested in the population. So if you go to C3 instead of B3, and we just want the first one, it's an 8. And all it's telling us, it starts off with an 8, which is what we need for Benford's law. Remember, Benford's law is only about the first number in the data. So that's the code. I did it in there, and I dragged it down all the way 7,729 rows. That took about 5 minutes, which is a long, long time. Right, now what does this do? This counts everything from F3 to F7729 if the first digit is a 1. So basically it tells me how many of these numbers are 1. And when you drag it down, it will do it for 9s, 8s, and so on. And don't forget, when you do this for yourself, when you do the Fibonacci, that you need to put those dollars in there. If you don't, it's going to start looking here, then it'll start looking here, then it'll start looking here. It'll go down 1 every time and mess up the data. Now we're going to need a total. Well, before we do that, let's just think. More cities do start with, populations do start with the digit 1. So about 2,000 start with a 1. Benford's law says that 30% should start with a 1. The question is, how close are we to that? Click on the total box and go there, sum. To click in there and then down there. So there's 7,724 cities. Okay, and about 2,000 of those populations start with a 1. So in there, we want to make that into a percentage. So we've got nearly 2,000 divided by 7,724. And if I go to format and I chose number, it'll just give me like that. But because I set that up for you already as a percent, you just have to take that down to the bottom. So Benford's law tells us that 30% of UK cities' population should start with a 1, and we got 25%. So it's close, and it gets closer as you go down. Really close when you get to 9s. Now the only remaining thing to do is to draw a graph of this. So you need to collect only the blue parts. We don't want the count. So you hold down the control key, get that, hold down control key and get that. This is the part that goes wrong. It's a little bit messy on this. On this, if you got to go down and click the I column as labels. So what that means is that it's using the leading digit is now going on the x-axis, and it wasn't before. And we have to change the kind of graph to a curve. A smooth curve will be fine. So the orange one is the Benford's law prediction, and the blue one is what we got. Right, okay. The rest of it's just housekeeping. We have to put on some titles and so on. So chart and axis chart title, and we can say populations of UK cities. And we can put it in the middle and change the font if we wish. We might want to change the color of the font and make it easy to see, black. And we could do it for the Y and X axis if we want to as well. But maybe we should skip that because it's a bit awkward to. Yeah, skip that for the moment. Okay, now I've got my graphs. All you've got to do is copy that and put it into there. So populations in, we can link it or unlink it, it doesn't matter. And does it follow Benford's law closely, quite closely, or no? I'd say quite closely. So you have to delete those to describe how close the fit is to Benford's law's prediction. You can't explain why it does, because that's a mystery in mathematics that nobody knows the answers to. But we can say that it does follow Benford's law. And the one that I've got for you to do is the Fibonacci series. And I've done nothing on that. And I'm hoping if you work in teams and you're up for it, if you're up for a bit of a challenge, you could discover whether Benford's law applies to Fibonacci numbers as well. Okay, now a review. When data does not follow Benford's law, it is almost certainly cheating, unless the distance or difference between the smallest and largest number isn't very big, in which case it might not be cheating, or if the number has been allocated or given by people, such as library cards or telephone numbers. In all other cases that I know, Benford's law applies. And if you find that it should apply and it doesn't, that means there's some cheating going on, almost certainly. And we found out with UK cities that it does follow Benford's law pretty closely. Okay, gentlemen, Fibonacci is over to you. Now, I'll understand if you chicken out of this because it's not so easy. But don't take your eye off the prize here. If you are capable of doing this, you are already in the 1% at the top of the population. That very few people know how to do this. So I think it's worth spending a little bit of time on it, unless you're feeling too stressed. Try and get this working, and also together with your friends as well. Okay, people, hope you enjoyed that, and I will see you next time.